Welcome to The Explainer. Today we're going on a truly fascinating journey. We are going to trace a path all the way from a pivotal 19th century breakthrough in tactile reading right up to modern digital information theory. And at the very heart of this journey is an absolutely powerful universal concept called quantization. Okay, let's dive right into this. Here is our roadmap for today. We'll hit the noisy analog world, look at Barbier's flawed night writing, explore the 2x3 binary breakthrough, crunch the math of tactile quantization, and wrap up with achieving perfect cognitive economy. And, playfully speaking, this agenda itself is a bit of a meta-demonstration of our topic. We're intentionally breaking a super dense subject down into a discrete, bite-sized grid just to keep our own memories from overloading.
All right, Section 1, the noisy analog world.
To really appreciate this subject, we need to step back and think about how our brains actually handle continuous, messy sensory input. Because, let's face it, the physical world doesn't come neatly packaged. It is chaotic. To understand this, look at Helen Keller's incredibly visceral water pump moment in Alabama. Cognitive scientists view this as a precise cognitive boundary. Keller was experiencing this continuous, infinite-dimensional analog flow of sensation. The temperature, the pressure, the fluid dynamics of gushing water. And then, in a flash of pure insight, her brain successfully mapped that analog chaos to the rigid, discrete, low-entropy letters WATER being spelled into her palm. So what exactly happened there? Well, Keller's brain performed what engineers and mathematicians call quantization. Basically, quantization is the process of mapping continuous, infinite values to a much smaller set of discrete, finite values. By doing this, her brain essentially filtered out the noisy analog universe to create a perfectly stable, error-resistant symbolic coordinate.
And this brilliantly illustrates why our biology absolutely relies on this trick. Think about it. Continuous analog signals degrade constantly. Whether it's environmental noise outside or synaptic noise firing inside the brain, purely continuous information inevitably gets corrupted. By discretizing the world, by literally rounding minor analog fluctuations up or down to the nearest rigid symbolic coordinate, we create an essential error correction mechanism. It is quite literally how biological systems prevent memory degradation. We literally couldn't function without it.
Moving on to Section 2, Barbier's flawed night writing. Let's zoom in on a very specific historical attempt to mechanicalize this kind of tactile communication. Before modern Braille, there was Charles Barbier's night writing. Now, this was originally designed for soldiers to communicate silently in the dark. Barbier used this massive 12-dot system, but it had some pretty major flaws. First, it was entirely phonetic, meaning it completely missed proper spelling or punctuation. But more importantly, and this was a huge physical bottleneck, 12 dots were simply way too large for a single finger pad to read without moving. The reading finger actually had to actively scrub across the symbol, which, as you can imagine, drastically slowed down reading speeds. Which brings us to Section 3, the 2x3 binary breakthrough.
What's truly amazing here is how a literal teenager engineered a solution that became the first binary form of writing in the modern era. Louis Braille solved Barbier's physical bottleneck by shrinking the matrix down to a compact 2x3 grid, exactly 6 dots. This was an elegant snap of technological genius. It meant the entire symbol fit perfectly beneath a single stationary fingertip. And because it's binary, meaning each dot is either raised or flat, this 2x3 grid creates exactly 64 discrete binary states, including the blank space. But how on earth do you capture all of human language with just 64 states? Well, notice how the 2x3 matrix dynamically expands those rigid states into infinite communicative potential. Braille essentially hacked the system using multi-cell prefix rules. For instance, a .6 placed right before a letter means it's a capital. Or take the numeric indicator, dots 3, 4, 5, and 6, that completely shifts the semantic interpretation of the following cells, magically turning the letters A through J into the numbers 1 through 0. It is just a brilliant workaround. Okay, Section 4, the math of tactile quantization. Let's look at the actual information-theoretic math behind this brilliant tactile translation. Because honestly, the numbers here are mind-blowing. The human eye transmits visual data at a staggering physical bandwidth of about 10 million bits per second. The tactile channel of the fingertip, under 100 bits per second. I mean, that is a massive physical bottleneck. Yet, and here is the crazy part, reading speeds for both visual and Braille readers max out at around the exact same rate, 200 to 400 words per minute. Why? Because the brain's semantic comprehension rate, the speed at which we actually process abstract linguistic symbols, bottlenecks at around 40 bits per second anyway. The 2x3 Braille matrix is just so perfectly optimized that it maxes out our cognitive limits despite that incredibly low physical bandwidth. And what's really wild is how this 19th century innovation is directly driving cutting-edge science today. Modern robotics and neuromorphic engineering are using these exact biological principles to teach machines how to read Braille. Devices like the Evitech optical tactile sensor, they don't use heavy bloated cameras. Instead, they encode tactile events as sparse, spatiotemporal streams of discrete spikes. They are quite literally mimicking the discrete quantization performed by human skin to achieve low-power, real-time machine perception. It's fascinating.
Finally, let's wrap things up with Section 5. Achieving perfect cognitive economy. Let's zoom back out to the universal cognitive science that unites humans, our history, and our machines. We can really see the exact process of cognitive economy at play here. Step 1, a messy, high-dimensional, continuous analog input physically impacts the sensor or the skin. Step 2, discretization filters and suppresses all that chaotic analog noise. And step 3, what biologists call winner-take-all neural clusters, forcefully snap that data into a single, clean, dominant symbolic comprehension.
This entire process is deeply rooted in what we call cognitive chunking. It's basically the biological process of projecting a structural grid onto information, buffering it into manageable units so our brains don't just overload. The 2x3 Braille cell isn't just a reading tool for the visually impaired, it is the ultimate physical manifestation of cognitive chunking. It's a flawless biological hack for human working memory. So the ultimate takeaway for us today is that semantic understanding isn't just some magical floating connection to the outside world. It strictly requires a discrete structural alignment to extract predictable meaning from a totally chaotic universe. This quantization process isn't just a neat trick. It is the fundamental architecture of all symbolic thought, all language, and literally all digital logic we use today. I want to leave you with a bit of a provocative question to ponder. As we continue to build our entire digital world on these strict binary grids, are our brains naturally binary machines that fundamentally require discrete symbols? Or are we just forcefully formatting a beautifully analog universe to fit our own biological limitations? Thank you so much for joining me on this explainer today, and as always, keep looking past the screen.